So let me start with a couple of excuses. The first one is Nunu actually asked me to give this talk. And when he did so, I protested. There were for several reasons. First, most of the work that I've done in this area is now several years out of date. The work that I am actively doing isn't really ready for presentation yet. And furthermore, there are people who've been doing work in this area more recently, which is the reason why there's such a long author list, in particular Ryusuke Nobara and Nunu himself. I felt that they might actually do a better job on this talk than I could, but my objections were brushed aside, so here I stand, not surprisingly. So I'm in that sort of awkward position of telling other people about work that I haven't been as tightly coupled to as I would like. So that's the first excuse. The second excuse that isn't so much about my talk, but about the subject in general. The application of the gyrokinetic model to reconnection is still in its very early stages. In contrast to some of the talks you heard earlier, we are still wrestling with more basic issues. For example, benchmarks, trying to get the code to produce linear growth rates that agree with various theories and different limits, trying to get the codes to agree with each other. The annoying thing about benchmarks is when they don't work, you have to try to figure out why, and it can take a really long time, and that is exactly the stage that we're in. There are still some puzzling things related to physics that probably some of us would rather not be studying. Linear theory is not the most exciting thing to be studying in the sense that it breaks down very, very early. We'd rather be doing nonlinear problems, but nevertheless, we're still stuck trying to get linear growth rates to agree with or understand them. Anyway, okay, so I'm going to try to give you an overview of where we are. It'll include a lot of these benchmarks. It'll be pointing out some of these things that aren't working, things we don't understand. I'll be presenting some nonlinear results. The nonlinear results are still fairly fresh. They aren't always understood either at a physical level, but that's just where we are. Things are early, and it's not my fault. Okay, so there are actually two codes, results of two codes I'll be talking about, AstroGK and Gene. Gene is a relative newcomer. I've started working with Frank Genko and a student recently on that. But as you guys probably mostly know, these models solve the gyrokinetic equations for both electrons and ions. Typically they're 5D, but right now they're really 4D in the sense that we're only doing 2D simulations. Nobody I know of has yet turned to 3D spatial dimension simulations with the gyrokinetic model yet. It's valid for all K perp rho I and K perp rho E, which is useful for reconnection, at least so we think, because of the small layers that can form. AstroGK has a new and improved collision operator that can reproduce Spitzer resistivity and other collisional effects, allowing us to study, or allowing Ryusuke to study, collisional reconnection, which I'll tell you about. These codes have the magnetosonic wave ordered out. Delta BZ is the guide field, the out of plane direction. So in GS2, for example, delta BZ is calculated via this relation. Gene is currently trying to implement this. I'm told by Frank that they're still not agreeing yet. As far as I know, that's not a big problem as far as the comparison of these two codes, which unfortunately, as you'll see, they're not at the moment agreeing very well. All right, so here's an important question. When is the AstroGK model or the Gene model, as it's currently implemented, actually applicable to reconnection? This turns out to be a lot harder to really pin down than you might think. In general terms, it's not that tough. Low frequency, where I suppose I would argue that the d by dt should include the convective term, but that's an issue for debate. The perturbations generated by reconnection have to be small. Why is that? The way to think about reconnection in a gyrokinetic code is as though you were looking, for example, at a nonlinear electromagnetic ITG mode. You've got nonlinear physics in there, you've got electromagnetic physics in there. and you've got very small scales ranging from electron scales to ion scales. Just as these codes can model such phenomena, they can also model reconnection, but these rules apply. In other words, there has to be some sensible decomposition between a background plasma and a perturbation. And so these things have to be small. This is one place where the complexity enters, because you need to be able to, in order to really quantify when these things are true, you have to have a pretty good grasp of how big the perturbations are that are generated by reconnection, and that is not so easy. In fact, I think really a publication quality study of this question needs to be done, and has not been, where one looks at the scaling of the various quantities in different regimes, tests them against the code, and lays out clearly just when are the gyrokinetic assumptions valid. And finally, as I said, delta BZ is given by this relation. This assumes that the ions to leading order are in force balance. It assumes that the velocity is yes.
It might just be historically fun to point out that, as far as I know, and Peter's here, right? You over there, Peter? Gyrokinetics, one of the main motivations in the early days was to do reconnection.
Oh, really?
That's where it came from.
I didn't know that.
Yeah, but okay.
What do you mean by early days? It was to handle geometry, but probably
Between 78 and 80, I know of a couple of papers where people said, if we're really going to get a handle on tearing instabilities and the evolution of, and the discovery, whether or not there's magnetic surfaces, we need a theory like this, and they then work out gyrokinetics. So that was the goal then.
I had no idea. Anyway, so this assumes that ions are in force balance. Essentially, it means that the magnetosonic wave is faster than anything else in your system. And I'm pretty sure that in all of practically all the simulations people have told you about so far, that this is violated. This is violated, yes. So I think that I will tell you in a moment what the condition is under which delta BZ is given by this.
It's not that much violated, though. I mean, if I do a cut across the outflow, the reconnection outflow, total pressure balance is very well satisfied, even across that narrow layer where the Paul fields are.
Yeah, you're right. That's true, but for example, if you look at the dynamics of the electron outflows, for example, those really should be governed by, say, electron MHD in the sort of simulation you're looking at. Electron MHD is a solution of Faraday's law that would time evolve delta BZ rather than having delta BZ given by this. The delta BZ in your simulations don't care about the ions, right?
No, I'm sorry. Electron MHD, a version of electron MHD is derivable from gyrokinetics and consistent with this.
If you mean, so in electron MHD, the ion motion is completely ignored.
It's slightly
The motions are
ignored
fast.
In the full case, there's a little bit of ion compressibility that comes in.
But it's irrelevant.
But it's largely irrelevant, and mathematically, there is a limit of gyrokinetics at below the ion Larmor scale that differs from electron MHD by a coefficient in front of the whole thing, so it doesn't actually matter.
Well, let's see.
Completely consistent with this.
Well, but in electron MHD, dBz dt is equal to the z component of the curl of E. You have to time evolve that equation. And by time evolving that equation, you obtain Bz, which you can then extract the electron flows from using J is equal to the curl of B. You're not doing that
You are effectively doing this because delta Bz is like delta n, and delta n is like phi, and there's a d phi by dt in the right hand side of the gyrokinetic.
Well,
And
why don't we?
Take moments, you're going to get it.
Yeah, let's leave this.
Let's leave. This is a good
discussion.
technical
Yeah, okay.
point. Perhaps you're right.
Yeah.
It would be good if you are. Anyway, so these are just three conditions. Perhaps there are others that I'm missing, but so the good news is that I believe that for fixed total beta rho I T over T E, these can usually, with a few special cases that I won't bother to mention right now, You can ask me about them later. They can usually be satisfied if the guide field BZ is sufficiently large. So if you're willing to just let that guide field become as large as you possibly want, these become true. But there are caveats. The first one is that the required BZ might be very large, at least for these things to be strictly obeyed. There's of course always the argument as to whether they need to be strictly obeyed, whether, for example, it matters if you get delta BZ a little wrong. It might not make any difference, which is part of the complexity of this question of, when is gyrokinetics applicable, and then secondly, there are some important parameter restrictions, and nailing those down, like I said, is hard unless you understand totally how the nonlinear perturbations scale. All right, so let me just briefly look at this question. How strong does BZ0, the guide field, have to be? So here's a fluid, actually two fluid simulation with a weak guide field, sort of like in the regime that we've been hearing about so far. So there's the x direction is horizontal. So the field in the x direction is reversing across here. It's pointing to the right up here and to the left down here. So Bx is the component of the magnetic field that's reconnecting. Bz is the component perpendicular to this plane. That's the guide field, the one that has to be very strong compared to Bx. And By is the vertical component, which is the component that's actually generated by reconnection. And if you look just in the outflow region here, the component By is on the order of 0.1 or 0.2 of Bx. And for the purposes of this talk, I won't fuss with factors of 0.1 or 0.2. Anyway, we believe that the physics that's governing the electron outflows here is essentially Whistler dynamics. You get the magnetic field lines come in, they reconnect. There's a strong current here compared to out here. The electrons are frozen into the magnetic field. The ions are essentially, their motion can be neglected. The electrons are approximately frozen in. This strong current pulls bends the reconnected field line out of the page. And at the same time, just like a Whistler wave, the flows that were in the z direction are rotated into the x direction. That's the way a Whistler wave works. So you end up with flows into the board and flows out to the right of the same order, and they are very roughly speaking to within some factor, we believe, the electron alphane speed. All right. Anyway, so the question is, this is a simulation in the weak guide field limit. This, I would contend, is not contained in gyrokinetics. In particular, maybe you can convince me this equation is being evolved. If this is how you're getting BZ, I wouldn't think so. But at any rate, what you can do is if you think about the uncoiling of the reconnected field lines like a wave. Okay, so here's a reconnected field line. You think about that like a wave. You think about the movements of the plasma back and forth as a wave, and you ask, when does this condition become valid? When do the ions become an approximate force balance? And simultaneously, when does Whistler physics become irrelevant at all scales, even at the electron skin depth scale? What you can show from at least roughly is that you need the magnetosonic speed to be greater than this electron alphane speed, or when you just putting in what these are, this is a condition that BZ has to be greater than BZ is the guide field, has to be greater than the reconnecting field, and then there's a mass ratio here, so this is a big factor. Now, yeah.
So, but this condition is mathematically speaking, when you derive gyrokinetics, you must have this condition, right? Because you're treating mass ratio as an only unity thing, and delta V over D as epsilon. So this isn't. Once you violated this, in principle, you can't do electron gyrokinetics.
And that's fine because so what I'm saying is what I'm saying is you need to satisfy this in order for the gyrokinetic model to be valid. And unfortunately, if it puts a condition on BZ that means BZ has to be pretty big because of this mass ratio factor here.
But what he was saying is that it's pretty big, it's still considered to be finite number.
Yeah.
It's big in practice.
If it doesn't upset you, it doesn't upset me. I'm just warning you. 5 is, people sometimes talk about a strong guide field as twice the in-plane field, okay?
That's why I said 1,000 this morning.
Right. And it made me happy when Bill said, what about 1,000? I thought, okay, 1,000. I think 1,000 would be okay. All right.
But what's interesting here is that it gets better with large beta. Is it counterintuitive or not?
We probably can't have BZ over BX1 no matter, something else would go wrong.
You know, I bet you it's not as bad as this. Just
Well-
because, none of us have run simulations with that big a BZ.
Yeah. Thank you, Jim.
I think Whistler physics has pretty much gone away in a lot of the stuff we've seen. And so it looks like kinetic Alfvén waves.
Yeah.
And so, then it's pretty clear the Whistler has gone away. Now, maybe we're not doing a big enough mass ratio.
Well, but let me just say, if you look at wave physics and you start off with a wavelength of some perturbation, say a shear Alfvén wave, and you start to make the wavelength smaller and smaller, it'll transition to a kinetic Alfvén wave. That branch will then go away. You'll then pick up the Whistler branch at still smaller scales, and then that'll take you all the way down to the electron skin depth. So unless this condition is satisfied. If this condition is satisfied, you'll have the kinetic Alfvén wave all the way down to the electron skin depth and no Whistler.
So when you say you will first get kinetic Alfvén wave and then you will get Whistler, what is the timeline here? What are you changing?
Scale length, the K.
K perp.
K perp. K
K
perp.
perp.
K perp.
So you're just doing linear mode analysis and looking at the transitions.
At constant K parallel you're doing this.
I suppose, yes. Keep K parallel constant. Sure, I suppose you could.
But I think the
Saying
question, what he's saying though is if K parallel is not small, then you hit this cyclotron frequency and you jump from kinetic Alfvén waves goes away, then you get to Whistler.
It's no.
Before you get to K rho E of order 1. But if K parallel is small, then you get the other way.
Well,
I think K parallel you can regard as fixed and just consider K perp rho.
But the two regimes that you just described, I think are basically the degree of anisotropy, which is sort of what you're saying with BZ over BX.
Well, let me tell you the way I'm thinking of it. Maybe it's the same. I'm thinking keep K parallel V Alfvén fixed.
Yes.
The kinetic Alfvén wave dispersion relation is like omega squared is K parallel squared V Alfvén squared times 1 plus K perp squared rho S squared. All right, now let's start cranking up K perp, keeping K parallel fixed. K perp rho starts to get bigger and bigger and bigger and bigger. At some point, if this condition is satisfied, that dispersion relation of the kinetic Alfvén wave will be valid all the way up to K perp equal to 1 over the electron skin depth, at which point the kinetic Alfvén wave will roll over due to electron skin depth effects. If you don't satisfy this condition, something different happens. You reach a scale that is longer than the electron skin depth. The kinetic Alfvén wave goes away. A new branch then appears, which is the Whistler wave, which is connected to the magnetosonic branch rather than the shear Alfvén branch. The Whistler appears. That then takes you all the way down to the electron skin depth. So if you don't satisfy this condition at the electron skin depth scale, which we think actually exists in the simulations, you should in principle have Whistler dynamics, which I agree with Jim, probably doesn't make that big a difference in terms of the total reconnection rate. And in fact, people who have been doing reduced MHD simulations have been ignoring this for years. I mean, all of these conditions I'm talking about also apply to reduced MHD, and it hasn't bothered anybody. The sawtooth doesn't obey this condition.
Barrett,
Yeah.
what is the scale at which you claim you're going to go from kinetic Alfvén wave to Whistler? Is this when the omega hits omega cyclotron? Is this what you're thinking of?
Does it do that? I'm not sure. It might be that scale. I can show. We wrote a paper about it. I've got it.
Yes, I'll argue with that.
I'm not sure. I know. I can tell you. In a second, I could look it up and tell you what it is.
And Barrett, if you do the scaling a little differently, you just say K parallel is equal to K times BX over BZ and do it that way, do you still have the same issues?
Yeah,
In
so.
other words, keeping K parallel fixed is probably not the way to compare to a 2D simulation, because K parallel gets smaller and smaller.
Yeah, so K parallel V alphane is KX VX in these simulations.
Okay. So the scaling you're talking about, that description, use this variable K parallel.
I was thinking of holding this fixed.
I know, but that's why I'm asking you. 'Cause
Uh-huh.
In reality, if you're comparing to a 2D simulation,
Oh.
K parallel is going to vary as you go through these scales.
Yeah, to my knowledge, everything I said still applies.
Okay.
Scaling would be different.
So,
Yeah.
so what you get is a mode conversion from kinetic alphane wave to Whistler?
The kinetic alphane wave branch goes away, and the Whistler wave is picked up. There's a very interesting and confusing thing, which is at high beta,
Yeah.
the dispersion relation for the Whistler becomes identical to the dispersion relation of the shear alphane, kinetic alphane wave at high beta. Instead of rho s, it's the ion skin depth that appears in the k squared rho s squared. It becomes k squared di squared. So you're in a situation where you've got an identical dispersion relation, but they apply at different scales. The shear alphane branch, the kinetic alphane wave branch applies at longer scales and lower wavelengths, and lower frequencies, and it's that lower frequency that allows the ions to be in force balance. So for kinetic alphane wave, P wiggle plus BZ wiggle, that's always satisfied because the ions are to leading order in force balance. When you transition to the Whistler, the electrons, the ion force balance becomes completely irrelevant. The ions are just they can't move, they are not moving. The electrons are doing everything, and it's like electron MHD. But you have the dispersion relation, the relation between omega and K is identical.
Yeah, it's odd. Just
It's
because
odd.
They have different polarizations, so that they would somehow help each other.
It is odd.
That's right. I mean, weird things like that happen at mode
Yeah,
conversions.
well,
It'd be interesting to see. You said you wrote a paper about this?
yeah.
Okay.
Yeah, they are separate branches. The Whistler branch is an outgrowth at high frequency of the magnetosonic wave, whereas the kinetic alphane wave is the shear alphane.
You haven't done this slide yet.
Yeah. All right. So I said, in addition to my gloomy statement about BZ, I said that there can be parameter restrictions that are important. Okay. And so here I thought I would give an example of this. So suppose you consider our good old low beta friend with a large guide field, the typical case where one would use a reduced MHD model to study, say, sawtooth crash or something. The Ademir paper, for example, the one that was referred to earlier. In this situation, typically the density is given by the polarization density, where rho s is just CS over omega Ci. The temperatures actually cancel here. It's a little tricky. If you work out if you put one of the del perps on the phi to give you an E cross B, and you put the C over B's in and everything, this is exactly equal to this. Okay, so this is the typical magnitude of the density, the nonlinear density perturbation in in a strong guide field simulation of the type that we've been talking about up till now. Okay. All right. So first you think no problem. We're golden here because we got an omega Ci downstairs. So I let BZ get very large. This is I'm going to wipe this is going to make it small. And therefore, reconnection is indeed just little ripples on the background plasma like we want. But of course, it depends on how big VE is and how big K perp is. And just to take sort of a conservative estimate, you can reach K perps on the order of 1 over OS without too much trouble. And a natural choice for VE would be the alphane speed based on the reconnecting component. That just happens due to the release of magnetic tension. The field lines come in and they go shooting off at this alphane speed. This is what everybody assumes. Anyway, so take this, plug it in for VE, and take K and put it 1 over OS. And rho s has got a omega Ci here. So the omega Ci's cancel, and this is equal to this. And CS over VAX is this, the square root of 2 over beta based upon the reconnecting component. So at least And let me just say, this is conservative. You can get velocities larger than this, for sure. And you can get scale lengths that are smaller than this, definitely. And
But those small scale lengths, the initial
Still okay.
n doesn't go like a plus and phi. It goes like 1.
yeah. So you're right. Well,
five.
it depends on what TI is. So
But you're
if
taking TI small.
if TI were small, this would always be true. But you're right. If TI were over TE, you get an adiabatic
Yeah.
ion response.
Hold on.
But if TI is equal to TE, actually, then you get the same. Since I'm assuming K perp rho is of order 1, you can either take an adiabatic electron ion response, or you can take this. They'll give you the same, because I'm putting K perp rho s equal to 1 here. So for in that case, it doesn't matter which way, whether it doesn't matter the fact that you have this operator order 1 because of this assumption. Anyway, so let me poll the reconnection experts out there. This seems consistent with my intuition. When you do a guide field simulation, you get a sort of quadrupolar electron pressure perturbation density. In order for that to be small compared to the background, well, typically it isn't, right? Because I've done many simulations where this is of order unity, and in that case, I know that you can get a substantial cavity or enhancement of the density due to this effect. This is proportional to the vorticity.
But this is in your famous paper, Barrett. The same condition, right? Your diagram.
The previous thing was in my paper. This was in a. This is in a paper that we wrote. This is a different paper.
This is the PRL paper, and then precisely this condition was in there.
The other one was a PRL paper. This one only made it into JGR, the one that had this one in, where it was called Signatures of Collisionless Reconnection, and we went through all the different parameter regimes. Yeah, you can have a quadrupolar VZ, you can have this, you can have that.
That's the 2001. If it's
Yeah.
only in JGR, it doesn't have to be satisfied, right?
I thought the space physics people would be interested in it. Everyone was obsessively looking for a quadrupolar V out of plane field, but you don't always get that. And only in some circumstances. So anyway. All right, linear theory as advertised. The details aren't too important. I'm looking at an equilibrium that's sinusoidal. This is not a big simulation. The total length so you've got a sinusoidal field that reconnects, and the wavelength of this equilibrium sinusoidal field is 10 pi times rho SE, which is rho SE is just the ion Larmor radius based on TE, which gives a kx is the equilibrium wave number, which gives a k perp rho SE of 0.2. So this is not an ambitious simulation, but this is the first thing that we tried. And we've got some other auxiliary variables that aren't too important. A normalizing factor, gamma A, delta prime, which turns out to the left of the figure is the small delta prime limit. So if you want to say like the sawtooth crash, you're down in this region typically. The delta prime equal to 0 is right at this point, and so which is consistent with the fact that the growth rates are going to 0 there. Turns out this is going to be a killer numerically compared to this regime, as I'll show you in a second. Anyway, so we have a bunch of different curves here. First, consider the case of small TI much less than TE. The gyrokinetic code gave the black crosses here. And I was pretty happy about that because some kinetic calculations, some of which I think Jim did, this was one of them, and that was another. And then later Fitzpatrick came along and unified them in a fluid calculation, and we solved that, and we got this curve here. Everything seemed reasonably close. I thought the agreement was pretty good. But then we turned on TI, and when we turned on TI, it was very surprising. In the gyrokinetic code, we got almost no change in the growth rate when we cranked TI up to 5 TE. That was as far as Paolo and I were willing to go. Ryuska has since pushed it up to like a factor of 100 10, 100, TI over TE? What's the biggest value of TI over TE? 10. And you didn't see much of an effect. So it's like TI isn't doing anything. The calculations kind of disagree with this. The calculations typically enter as TE plus TI, or sometimes TE plus the ratio of specific heats times TI. So usually in either this limit or this limit, there's a rho s to the 2/3 here, there's a rho s here. The theory predicts that as you increase, if you hold TE fixed and then you increase TI, the growth rate should go up. So so you go from this curve, for example, to this curve. But the gyrokinetic results, which are the blue triangles, don't move. And there are two different mass ratios here, and we found basically the same thing. So that's one of the problems that I was telling you about. You do a benchmark and it doesn't work. You want to try to figure out why. Well, it got worse recently. We brought in another. Frank and a student. Let's see. It's Moritz Puchel. Am I saying that right? MJ. So this is gamma MJ. This is gamma Rogers. So he generated these curves. So he looked at, for TI much smaller than TE, this is what Gene was giving, so it wasn't too terrible, but then when he cranks up TI, rather than the growth rate going up, which is what I was expecting, the growth rate actually goes way down. So, so we don't know. We don't know what's going on here. We're struggling with the beast. I mean, we're sending emails. We're like working over the normalizations. You know, we're just like it's just. Beta is 0.2.
And the mass ratio?
Mass ratio is 100, 25.
This is real beta as opposed to beta.
That's the total beta.
So if it's 0.2, then delta B parallel is presumably no.
See, now that's what I thought. Okay, delta B parallel, it could be that because Gene doesn't have delta B parallel yet. And beta's not that small. But Ryuska did a scan. We also did a scan, which I kind of, it doesn't hardly change at all. So when we turn off delta B parallel,
Now, it's with and without delta B.
with and without, we turn it off. When we turn off in GS2, it changes things only very slightly. So it doesn't appear to be delta B parallel. We only tested one point, I think, like that one or something.
What physics is Gene?
It should be the same. I mean, there are, yeah.
When you change the temperature ratio, though, you keep the thickness of the layer constant in terms of like ion scales, or what?
The equilibrium current layer is just it's a sinusoid, and we're keeping that fixed.
And it's relative to what?
We're keeping kx times rho SE, which is rho s based on TE, equal to 0.2. So if you think of holding the electron temperature fixed, which is what we've been doing, we set T equal to 1. That doesn't change.
But the amplitudes are normalized to TE or TI?
In GS2, you mean? So we've been, we think we've been careful to correctly account for all that stuff. Yeah, you know, the normalizations are just such a, yes.
Even on the top case, the disagreement isn't just a constant factor. These curves have different slopes.
Yeah.
Right?
Right.
So does any of them go as 2/3 and the other one not?
These are the only results that I know about so far. So
Barrett, which one's KY? Which direction is that?
Y is the direction. I think I was calling it. Yeah, that's right. KY is the direction along the layer.
Which is the reconnecting field?
The reconnecting field in these simulations is BY,
Okay.
No.
So you
which is I've switched. That's because there's a difference in notation. In the tokamak world, everybody chooses the Y direction as the reconnecting field. In the other transparency, it was reversed. It's the thing that you can choose to be anything you want, not the equilibrium.
If you look at the structure of the layer, when you're changing TI, is the ion Lam radius compared to the layer thickness? I I mean, the line radius must be changing size compared to the layer, right?
Yeah, it is.
And are all these theories have full FLR effects in them?
They do. So interestingly, the growth rate in GS2 is like dead as a doornail to TI, but the eigenmode is not. And in fact, the eigenmode does what you'd expect from the linear theory. If you work out the linear theory, what you'd expect to find is that if you look at E parallel, just one of the many things you can look at, if you look at this, the spatial structure of E parallel, so now X is the direction perpendicular to the reconnecting layer, so it's the direction over which the sinusoid is varying. The ignorable direction is Y. What the linear theory says should happen is that when TI is much less than TE, E parallel should have a two-scale structure with an inner structure given by this scale length, where gamma, you have to put in what gamma is. Also depends on K. But then if you go into the other limit, then this inner scale length structure of E parallel, according to the linear theory, and according also to the code, should go away, and you should get rho s, which is the same as rho I in this limit. So AstroGK does exactly what the linear theory seems to me says it should do. It goes from having this really tiny little narrow spike at small ti to having a nice broad structure at high ti, but the growth rate doesn't seem to care about that. So this is a depressing picture to me.
Poor guy.
It's a convergence study that Paolo did. Yeah, and it's for a mass ratio of 100, and it was looking at how fast does the code converge to a stable growth rate as you change the number of modes in the x direction, which is the direction perpendicular to the layer. So it's the direction in which you've got these really thin layers, so you need lots and lots of resolution. And the proper growth rate curve that I actually showed you earlier goes through, looks like I should have put it on here. It goes like that. Yeah, so look at any of these points here. Yeah, blue diamonds or red or the red. And so the thing I learned from this was, so if you go to the linear theory and you say, what is the smallest scale length in the theory? This theory just is pretty unequivocal about that. It says that it should be this scale length delta that I was talking about a second ago, where of course you got to know what the growth rate is. But if you compute the growth rate and you plug it in here and you know what value of ky it is, which ky is the thing that's running on this axis, you can compute what delta is. So we know how big delta is for all these different points, and we also know what value of nx you have to go to in order to get convergence to the growth rate. For example, here you get pretty good convergence when nx approaches 256. 256 is the, you're going from like a green circle to a square here. So you're going from a green circle to the square, you don't get much of a change. And then if you refine it further to the asterisk or the diamond, you get exactly the same value. So you get convergence here at nx of 256. If you define kx as 2 pi nx over lx, where lx is 10 pi rho c, that's held fixed in all the simulations. And then you compute delta by this formula using the correct growth rate. What you conclude is that you get convergence at this point when kx delta, where delta is that smallest linear theory scaling, is about 7. Okay, well, now you go over to the other side of the curve, and things have gotten much worse. In order to get convergence over here, you have to go up to something like nx equal to this or this. And the reason, at first I thought something that this didn't make any sense, but when I actually computed delta, I realized that it was actually the same thing we had over here. In other words, the expression for delta contains a factor of the growth rate, and the growth rate is going to 0 as you head toward this point. This is where delta prime is equal to 0. And as a result, delta gets smaller and smaller and smaller. And as a result, you need more and more resolution. And in fact, 4096 corresponds to a kx delta of 8, which is just like over here. So at least as far as the linear theory is concerned, it seems like you need something on the order of kx delta, where delta is your small scale, on the order of 8 or something like that. But anyway, the reason why this is depressing is this is a very big number. So if you want to do full-scale nonlinear simulations, and if you think that you need to resolve this, and I'm not sure if you do, but the linear theory you do, then you're going to be dealing with big simulations, and this is a rather small box. It's only 30 rho s. This is just something I'll touch briefly on. I got a call from Richard Fitzpatrick one day, and apparently he and Vladimir Murnov were having a knockdown drag-out fight over the electron gyroviscous cancellation. And it turns out that if you do the theory with ignoring the electron gyroviscous cancellation, the theory comes in with a quadratic growth rate, whereas if you include the electron gyroviscous cancellation, you get a straight line there. Anyway, they're still arguing about this, and they're asking us to do simulations to sort that out.
But you have the simulations there.
Yeah, so it's complicated. I'll tell you about it. It's not that interesting, but it's
Tell
kind
us
of.
who's right, Fitzpatrick or Murnov?
Vladimir thinks that the electron gyroviscous cancellation is only partial, but there's something else that happens that makes the result turn out to be correct. And that's where I think their disagreement is. Fundamentally, it's whether or not you're allowed to assume that the velocity is to leading order incompressible, which when you do the normal gyroviscous cancellation calculation, everybody always assumes that the div v to leading order is 0. Murnov says that is not correct in this limit.
The dashed line, whose kinetic theory is this? What is this?
Oh, this is well, it's reproduced in the back of my 2000 of this paper that has all these results in it. The person? No, this one's not so famous. This is the one that this is.
You can still be the first to cite it.
This, yeah, I'm saying that's where you. That's where you can look to see it. I don't know who first derived it. I know that Porcelli has a derivation of it. I think it's probably pretty old. This if you're asking me about this, I think it's. I've definitely cited it in my paper, and it's old, and I don't remember. Yeah.
What am I missing here? Why should that fluid theory be valid? I mean, these are crude phenomenological closure schemes normally, with lots of approximations made to get a vorticity equation, including this gyroviscous business. So why is the gold standard the fluid theory? Why should you agree with fluid theory?
Well, okay,
why
so.
aren't you comparing it to a full simulation like Bill?
Which we should do. Because I was thinking, actually, I would like to give Bill a homework assignment, Bill Doughton.
But this is all just collision, you're in the collision.
Collisions limit, yeah.
And in terms of like the way I talk about guide field, how
Yeah.
big is the guide field?
Well, so we're in this asymptotic limit. So we don't have to say how big it is. It's not, you can actually, it's like a reduced MHD simulation where it gets ordered out, and it can be, once it's beyond a certain value, you can just.
You're supposed to converge to this if you keep making it bigger.
And if you
But-
could tell me what parameters
yeah.
to pick, then I could compute the eigennodes and.
Right, and I was thinking as you were giving your talk,
They would fall.
me too. I was thinking, all right, maybe finally, with this TI, but back to Peter's point, you're right. Yeah, so totally collisionless. No hope of any rational closure there. But the theories that that produce this line and this line actually purport to have more kinetic theory in them. I'll talk about it in a second, but they're not based on just the fluid equations. It turns out, for reasons that I won't bore you with, that the fluid theory gives practically the same answer. For Ti equal to, well, actually no, if you choose isothermal ions and electrons, it gives exactly the same answer. Both in this limit and in this limit.
Does PS2 include trapping?
What'd you say?
Does PS2 include this electron trapping?
It does, yeah.
He means in the field, electrostatic trapping in the wave.
Yeah, but what parallel electric field you have?
Oh, maybe not, yeah.
We don't have that. no.
That's right, that's right.
We don't have that.
You've got trapped particles in the equilibrium. All right, so now I'm transitioning to work that was done by Ryusuke Numata. He was looking at including the resistivity. So, and I never did answer. Well, I did. Okay, I'll come back to the question of the kinetic theory in a second. Anyway, so he's looking at things now in the collisional limit. So these are plots that Ryusuke made, and here's the Lundquist number. So it gets, on the order of 10 here, all the way up to something pretty big. The gyrokinetic results are for different betas are these points here. The two fluid model is shown by these curves. And it's for yet another equilibrium here, mass ratio of 100. TI equal to TE, although if you crank up TI or set TI equal to 0, I think you get pretty much the same answer, right? So what we're currently debating about is whether or not we should be upset about the fact that we're not reproducing the fluid theory in the small Lundquist number limit. So what's your opinion about that? I mean, is the collision frequency over here really big enough? Is it larger than all the growth rates so that you'd expect an isotropic pressure and all that stuff that the MHD theory is based on? Or
I don't know. I didn't compare the collision frequency with other frequencies, but I just found out the collisionality
as much as possible.
Yeah. Then I just don't get the carrying growth rate. It's just sorry.
Okay. Well, so
Work though, right? I mean, in a way, it's disturbing if it doesn't work.
I'm not sure.
Well, I mean, often, if you I haven't looked at reconnection papers, but we've looked at this edge physics, then a lot of times the fluid descriptions are based on a Brzezinski description, which leaves a lot of physics out of it. It assumes the high flow watering, it doesn't do the gyro viscosities or the collisional viscosities in any sensible way. Because when you have lower
None of those in the collision. Well, in this strongly collisional limit, where your sweep Parker layer is much larger than rho s and C over omega p and all those other scales, I'm not sure you would expect any of those things to matter.
All the flows near sonic, the Brzezinski waters everything, all of the flows near sonic.
This is just straight up resistive MHD, right? This isn't Brzezinski. This is just resistive MHD.
But that's what the resistive MHD comes from.
Turn up viscosity. So if you turn up collisionality in gyrokinetics, you should recover reduced MHD, basically, right? I think on paper you do.
No. It depends whether your ordering is in the high flow or the drift limit, what you're going to recover.
Well, this would be the high flow limit, though.
Is what?
Gyrokinetics is all drift.
Yes,
Yeah,
and the fluid
gyrokinetics all
theory
drift ordering,
is
so
large flow.
No, I'm saying if
So
I
you'll
take.
recover a low flow version, you won't cover,
No,
you'll get things like gyro viscosity coming.
Yeah, but if I take gyrokinetics and on paper turn up collisionality, I will discover reduced MHD.
No.
Yeah.
Well, a low flow version of reduced MHD, you won't get the high.
Just
You'll get
standard reduced MHD.
Well, this is exactly the kind of question that the discussion that I think I was hoping for us to have here. So is it past my time?
No, keep going. I think we'll just transition your talk right into the discussion.
Okay.
So you'll be leading the
So you can cut me just go like that now.
Well, but it matters.
How much do you have?
If gyro viscous
Um,
then you have to be careful.
I'll be quick.
But usually the gyro viscosity things come in at the same order that V dot grad V terms come in.
But you can order electron collisions and ion collisions differently.
In the drift ordering, they're comparable.
But if you order electron collisions and ion collisions differently, you make electrons very collisions, get your MHD and viscosity very careful.
But I think, Alex, it's still, I'm not sure, and I guess it doesn't sound like any of us are sure whether or not we're in a regime where it should converge to reduced MHD or not. Whether we're there or not, I guess we're not sure, right? Or are you sure? Have you checked have you actually checked the numbers and
I'm
all?
not sure these simulations are.
Right, so that's what I think we should check.
And even if we are, you have to be very careful that the equilibrium isn't radically being changed by the collision and confusing the answer, because if the equilibrium is decaying the equal fast because of these large collisions in the low Lundquist number limit, then you'll get a different growth rate because you're
No, but
looking
the
at
Lundquist
different
number is being
instability.
sourced. The equilibrium is being held fixed by the source. So it doesn't confuse out in these simulations. There's an electric
There's
field.
subtlety in that, exactly how that works. I agree that that's what we're aiming to do, but there's subtlety. We should do it.
So one idea that's been put forward for this disagreement with the TI business has to do with the fact that simple adiabatic or isothermal equation of state isn't right, which isn't surprising. And this plot tries to show that Ryuska made. So it's for 3 different parameter regimes. Capital gamma is the adiabatic index. So it would be 1 for isothermal and 5/3 for isotropic. And the red curve is the perpendicular gamma for I. The green is the parallel gamma I, and ditto with the electrons here. The one that I zoomed in on first was gamma perp I, because that in the calculations, that's where the TI terms come from. Typically, it's PI perp. It's coming from TI perp. So that's this red line. Maybe I'm wrong about that, but that's what I thought. So it seems to be isothermal in the center, then zooms up to 4. Of course, if you took a gamma equal to 4, it would strengthen the TI dependence of the growth rate rather than weaken it. But maybe that's wrong because of the spatial variation or something. Or I'm just showing you this because some of us think it's important. I'm not sure.
So these Fitzpatrick theories and so on, they all assume some specific value of gamma, right?
Right.
Some constant value of gamma.
Right.
And do they assume gamma 1 or something else? After all, in the electron layer, or in the layer there, it certainly almost looks like taking gamma close to 1 might be sufficient.
Which is what I would have done. I think they choose isothermal electrons.
Yeah. Yeah, that's right.
Well, if you had isothermal electrons, then indeed, and low Vega, then indeed everything would be flowing.
Yeah, there is this little blip in here.
And there's a purple blip.
Oh yeah, right. That's depending on whether you think that, and actually there is a PE parallel, of course, in Ohm's law that's important, right?
So that's telling you you're not isothermal, and therefore you are kinetic. That blip is basically.
Well, you're not isothermal,
Mhm.
meaning you were kinetic at that point.
Well,
There might be a perfectly good non-isothermal fluid law, which would
no, but kinetic electrons come through delta TE parallel. And
I
that's
understand
exactly-
that meaning of the word kinetic, right?
Yeah, although
What's you've got, those several curves correspond to different models, right?
there's 3. These are 3 different parameter
Yeah.
cases.
Yeah.
The red and the green are ions, perp and parallel, and the blue and the magenta
And that's
are
in the gyrokinetic
electrons,
right?
and that's taken directly by I guess just calculating p wiggle in the gyrokinetic simulation, dividing by that.
What about the Jaeger-Dallas equation?
That would give you 2.5 inside the layer and 0.5 in the curve.
I mean, I'm not. I mean, looking at this, my first reaction would be, well, okay, yeah, obviously constant gamma is not the greatest, but at least qualitatively it doesn't look terrible. But apparently it's terrible. I mean.
It's just not thinking with gamma, you're admitting you have a phenomenological description of the field.
Yeah, I guess
There's
the
nothing
gamma parallel
You're right. You typically the kinetic calculations, I believe, typically assume just assume
even the ion.
isothermal.
I'm trying to make you less depressed. It seems like you're making comparisons against something that's doomed to failure.
Well,
That's what make him less depressed.
Well, if you were comparing it against the kinetic results, you might actually be doing things right. That's the goal.
I'll just maybe you're right. There have been the kinetic calculations we're comparing to have been around for decades. To me, when somebody comes along and says, "Oh, those calculations are all wrong," it's kind of a surprise.
What if they agreed with Jim's calculations and Bill's calculations, but they do kinetically, and you gyrokinetically, you'd feel better, and I want you to feel better.
But Jim, I believe that I believe that the kinetic calculations, which have shortcomings, they give the answers I was showing you, the disagreement that I was showing you earlier, as far as I know.
They do agree?
They disagree. They have the same, they change, basically what happened, Jim can correct me if he knows better. When you include TI, generally it just changes TE to TE plus TI.
You're talking about the analytic calculation.
Yeah, which you can do it, let's say at the large delta prime, for example.
See, that just can't be true for the gyradius part. That's true for pressure effects, but for gyradii, K per rho I is its own parameter. So that makes me nervous.
Yeah.
Everybody here is so good.
Yeah, let's see, did I have anything here? One thing I didn't mention was that the TI dependence in the fluid, so where does this TI dependence come from? The TI dependence in the code, as far as I can tell, is the same as the TI dependence you get in the kinetic Alfvén wave. So the TI that appears in here is the same as if you take the reconnection linear equations and you just make the magnetic field homogeneous, you get this dispersion relation. And the TI terms are the terms that are in rho s. And for K rho I much greater than 1, you can trace that back to an adiabatic ion response, and the fluid model gives the same thing. Anyway, so so now I'm turning on to nonlinear results. I'll just quickly say what some of these are. Of course, nonlinear is the most interesting case, but there hasn't been too much work done on it yet because we're still struggling with these other questions. But I was surprised that the nonlinear GS2 for that sinusoidal equilibrium produced nearly identical results to our simple totally isothermal two-fluid model with zero collisionality. There's still no ion temperature dependence, but there wasn't any ion temperature dependence in the fluid model either. And this is for a large delta prime case. I'll show you a small delta. Actually, are your simulations? Your simulations, are they small delta prime or large delta prime? Nonlinear ones. This one.
So here
That
there's
one.
dependence on the temperature ratio.
Yeah. So nonlinearly, neither, and this. I mean, we've been aware of this for some time, that the fluid code doesn't, what it cares about, it doesn't care about the temperature ratio very much. Or maybe,
So
I don't know, maybe.
where's the mystery? If all the codes agree that TI is irrelevant.
No.
Forget. Set that aside. Set that aside for one moment. He's new to the game. All the codes have been trying to do this problem for more than 3 years. All agree that TI is irrelevant. Maybe we need to think about why we think it's supposed to be relevant.
And I have, you're right.
You keep running
Too
GS2
fluid.
and keep telling you, it keeps
Too
telling you.
fluid.
Well, okay,
Yeah, but
the nonlinear,
That's just a nice comparison, but it's not a benchmark, right? I mean, that's just sort of informational.
I guess what I'm asking is why do you think TI matters?
Well, but
the kinetic calculations, which have approximations in them, and maybe they make wrong assumptions about TI, predict enhancement of the growth rate with TI. And we basically see nothing with TI, and Gene sees a depression.
But kinetic calculations being linear.
Kinetic linear, I mean linear theory. And generally they're designed so that all the ones I know of are based on an approximation to the ion response that's a Pidé approximation that's valid at small k perp rho I and large k perp rho I, and then just make some simple. There's a weird thing for TI much greater than TE. When we found one thing that I had never seen before. Paolo found this. So when we were doing very low noise simulations for this high TI case, so essentially this curve, say this blue curve here, the one that seems to go so nicely. Well, if you don't seed this simulation with enough noise, it doesn't do that. it saturates. It saturates at about an island width on the order of rho s, like here. If you put in noise, apparently this saturation mechanism, which we never figured out, is fairly fragile if you put in noise. It continues to grow and becomes that blue curve there. Is that right, Paolo? Did I say that right? All right, here, this is new. So diamagnetic stabilization might be important for the sawtooth crash, and some people I'm working with, Amitabha Bhattacharjee.
The previous one it was shown, is the mode frequency different?
Is the mode frequency different? I think they look, well, does the island drift at all when it saturates, or just sits there? Just sits there. So the mode frequency is 0 in both cases, approximately.
And the collisions in those two cases?
0.
In both cases?
You know, 0. Yeah. Yeah, sorry. So diamagnetic stabilization, if you have an ambient pressure gradient across the layer, it generates a diamagnetic drift that is parallel to the layer, and on one side it'll oppose the ion outflow, and on the other side it'll amplify it. And if you turn it up enough, it's been shown in two fluid calculations and in particle calculations that if you turn up the gradient, pressure gradient enough, you get nonlinear saturation. So we've succeeded in reproducing that with Astra GK. The catch is that we seem to need a much larger value of the gradient in the gyrokinetic model than in the two fluid model. The particle model was run with a slightly different magnetic geometry, so I don't know yet how these compare. So this is just very early work, but that's one of the things we're looking at. So this is a fully nonlinear problem. This is essentially nonlinear saturation here of an island. And then here's this is near the end. So Ryuska not only did the linear work, but he's started to do some nonlinear stuff. The gyrokinetic results are the nonlinear resistive, so there's fairly low Lundquist numbers here. So you've got the gyrokinetic results in green, and they saturate at a lower level. I guess that's the bottom line. That's about all we know at this point, unless there's something else you want to say. And those are just, I won't go into details there. All right. Anyway, so there you have it. It's a work in progress, and it remains to be seen, I think, how exactly the gyrokinetic model will contribute to the subject, but it will take some time.